আছে নেকি ক'তবা এই কুৱেশ্যনৰ লিষ্ট So many of you did that, but a common mistake, I don't know why. So the complete angle is 2 pi, right, or 360. So this angle must be 1/6 because there are 6-sided, right? So this angle, let's call this phi. So phi must be the whole angle divided by 6-sided. Okay. All right. So here, let's say the number of sides n equal to 6. Okay. Then, in case of a wire, long wire, from some point A to B, if this is the perpendicular, then we actually need two angles. One is this angle, theta 1, the other is theta 2. Okay. If it goes down, then it's negative. So in our case, this is the perpendicular distance, which is S, and this angle and this angle are same. So our theta 1 equal to what? Phi by 2, and theta 2 is minus phi by 2, right? So this is pi by 3 then. So this becomes pi by 3 by 2 equal to pi by 6. This is minus pi by 6. Okay. So then you just need to put in the formula. Sin theta 1 minus sin theta 2. But none of you really write exactly what is going on. You should. Because in the exams, if you directly put some formula and something, they don't know what's going on. What is theta 1? What is theta 2? What are these symbols? Okay. So you need to write because nobody knows what is theta 1, what is theta 2. You need to draw the diagram clearly and mark the angle. Say that this formula is coming from that, where the upper angle, and these things are important. I understand because we went through this, but whoever is checking your paper will not understand. Anyway, so mu naught by 4 pi s. This is what? This is for just one side, let's say. Okay, so let's call this, let's say A0, A1, A2, A3, A4, A5. Just a useful notation. You could say A, B, C, D, E, but then when we have like more than 26 sides, then you run out of letters. What? Oh, Magnetite, of course. Current to lagibo nohole magnetic field korpora aibo. Just a loop cannot give us magnetic field. Okay, so this is let's say just for one side, for A0 A1, just to be a. Okay, and every side, because if this is current, then this is the current. So with the right hand thumb rule, you see that it's going outward, and therefore for every side it's really going outward. And magnitude should also be the same. That argument you should write in one line or so. And then you should say that the total magnetic field B equal to these 6 sides, right? So it should be 6 sides, so 6 times in general and into this. So basically, once again, these are theta 1 and theta 2 are going to be always the same, right? Because it's a regular hexagon or regular polygon. So you could just say that this theta 1 equal to theta 2 to minus theta 2 equal to some, I don't know, theta. Then this will become 2 sine theta. right? So your formula becomes mu naught I by 4 pi s to sine of, what is here, pi by 6, right? Or this formula in general should be total angle divided by n equal to 6 here, okay? So this is 2 pi by n, total angle divided by number of sides, that's your this angle. Then half the angle is 5 by 2, so I'm doing it directly for the polygon. Imagining that n equal to 6, then you don't need to change it again, okay? Total angle 2 pi, total sides n equal to 6 for now, it could be 4. So therefore, 2 pi by n for phi, and this 5 by 2, just 5 by 2. So, what is 5 by 2? 2 pi by n divided by 2. So that's just pi by n, right? So pi by n. So that is your answer for n equal to 6 or any n, right? Any n. Therefore, for n-sided polygon, this is the answer. Now, what happens when n is large? N tends to infinity. So, look at this. That as the sides increase, number of sides increase, these are becoming smaller and smaller, right? So the angle becoming really smaller and smaller. So when n goes to infinity, what happens to pi by n? Theta. Okay? This is what? Theta equal to pi by n basically, right? So when n tends to infinity, theta equal to limit n tending to infinity, pi by n tends to 0, right? Pi over a huge number. So this angle, theta, is almost 0. When n equal to exactly infinity, then it's 0. Therefore, this angle is very small. What happens to sine of very small angle? Sine of theta when theta tends to 0. It is actually theta. Right? So what is your theta? Pi by n. So in the limit n tending to infinity, your b goes to n mu naught I by 4 pi s to 2, and then sine pi by n becomes pi by n, right? So sine theta is almost theta. Pi by n is extremely small, the sine of that is just pi by n. Therefore n cancels out, and the answer is mu naught I by 2 pi s. Is, yes, I always forget about that. Mu naught I by 2 pi s. Pi over, yes, thank you. Mu naught I by 2s. Obviously, you can guess that when n tending to infinity, so n is increasing like this, right? At some point, it should become a circle. That's when n is almost infinity, right? What are you laughing?
I have not multiplied this n.
Yeah. Because, I mean, for the most of you, for 6 sides, you multiply it by 6 because there are 6 sided. And when are n sided, you just calculate it for a dot actually. So one side will become just a point, and that will be obviously 0. If you don't multiply by n, this will be just some number divided by n. and tending to infinity, magnetic field is 0. That makes sense. That just means that what is the magnetic field due to this point at the center? Obviously 0. When you sum over all these points, then only you get that thing. So this must match with the magnetic field of a circle at the center. We have the answer for when you are a bit up here, right? What was the formula for magnetic field of this loop at this point, at a height c, let's say? Do you have it somewhere written? Mu naught I. Here's some r. Here's some j square r squared to the power 3 by 2. And mu naught I, yeah, the r square niki. R square 2s. তলত আর কি আছে ইয়াত একো নাই আৰু okay, so z equal to 0 বহাব লাগিব, then we come to the center, right? This height must be 0, then we'll be in this situation at the center. So then if g is 0, mu naught I by 2 r square by this is 0, this is r cube, so basically 1 over r, so that's mu naught I by 2r, and r is as the same thing, okay?
So we have to write this thing also in the cycle.
Which thing?
Or just write that it looks similar to the.
If you remember and if you are confident that this is the magnetic field due to the circle at the center, then yes. If you see that there are 7 marks, then you do this. I mean, there are 2 forms of Ampere's law. Either this or this. Only 2 forms really. তোমালোকে Stokes law so you apply Stokes law wrongly and got something strange. Don't know why, but this is differential form of Ampere's law. Differential form of Ampere's law. And this is called integral form or Ampere's circuital law. Okay. It should immediately click that I asked for this, because use conservation of charge. That actually means use continuity equation. If you remember continuity equation, del dot J equal to minus del rho by del T. This is current density and this is charge density. It means that, I explained it earlier, that within a volume, hypothetical or not, if you take a volume like surface, and within which, if you have some charge density, if that charge density is changing with time, if it's decreasing or increasing, it means that those charges are going out or some more charges are entering. Otherwise, it's not possible. They cannot be like just vanishing within or increasing. So if they're going out, that means there is an outgoing current that is making this charge reduce. Or there is an incoming current that is increasing this. Okay, so that's why this means a conservation of charge. It's like fluid. So you have leaks in the volume, only then water current will come out of this, let's say, balloon, and the density of fluid inside will change. Now, next question is, Ampere's law imply that it's a what? Steady current. So, first of all, steady current means this must be zero. The current density should not be changing with time. This is the first condition. Steady. It's not changing with time. So this is 0 and del dot J must be therefore equal to 0. Right? So this means this is another way of saying steady current. And if you take del dot J here, let's say, so what is J? 1 over mu naught del cross B basically, right? From here, from Ampere's law, what happens if you take del dot J? What is the divergence of a curl? Divergence of a curl is 0, always 0. So this part is identically 0. Therefore, del dot J is 0. When del dot J is 0, it means del rho del T is 0. So the charge density is not changing with time, and this implies steady current. Okay? It's just conceptual. There is nothing much mathematics here, really. So when someone's asked, like, show that it's a steady current, then in the end you have to show that del rho del T is 0. And that also means del dot J is 0 because of the continuity equation. Because del rho del T is del dot J, opposite sign. And you know why it's opposite sign. If charge is increasing inside, then for a vector. The positive convention, it's a convention. If you have a surface like this, a normal going outward is positive to this surface. And something entering is negative. It's just a convention. So positive divergence means something is diverging from a volume. So del dot J is divergence of something, which means going out from the volume. It's going from, if it is going out from the volume, then it means charges are reducing inside, they're decreasing inside. And that's why this opposite sign. So this you must always remember. This is true in many, many fields. Electromagnetism. Whenever there is something conserved, this will pop up. Okay. Any sort of charge. It could be gas, number of gas molecules inside something. It could be charge density. It comes in also in fluid dynamics, continuity equation. You must have found it there. So quantum mechanics, you will see that this becomes a probability density. So maybe next time. So Ampere's law implies del dot J equal to 0, and del dot J equal to 0 from continuity equation implies del rho del T is 0. So it's a steady current. Find the magnetic field. For this, straight wire up to this point.
This converts semi-infinite wire.
Semi-infinite, at the direction of infinity 9.
One direction.
So only in this direction it's infinity. And this is completely half circle. So its center must be here. Okay? What do we have to do if the radius is r? For this part, it's pretty simple. So how was the direction of current? Which is okay, which is right. So thumb should be in the direction of current. So the thumb should be in the direction of current. So if you then do it, it will be outward. It's outward, and it's outward for every bit. So basically, olop oporot hole will be in trouble. Okay, slightly above this plane, and it's a complicated problem because you remember then it should not, it was for a circle. So for a circle, it was simple because it was a whole circle. So a point of kenekwa asil, eta kono tenekwa angle for this piece, right, in this direction. And then we had symmetrically all these bits, and that's why we got like all these points, and they all cancel out in this direction. So we had only this, and it was easy. But once you remove half of it, then it's a messy problem. You know, there is nothing to cancel. Even this side is cancelled by this part, right? This is the symmetrically opposite part, which is missing. So there is no cancellation here. Then you will get like this half cone. And then you have to do the complicated vector sum for that. But fortunately, that's not the case here because we are at the center. So at the center, everything is just outward. So that this formula will be half of the formula for a circle. And we just did that. So B circle, semicircle, let's say, was what? Mu naught I by 2S, right? 2R. So the half of that. So mu naught I by 4R. And then it's then for this wire. So for wire, for the current going up, we need theta 1 and theta 2. What is theta 1? 0. Right? Angle with this line, theta 1 equal to 0. And theta 2 minus pi by 2. Okay? So for this upper line, let's say, so be upper wire, mu naught I by 4 pi. So this R will be the same R. Then sine of 0 minus sine of minus pi by 2. So that's just plus pi by 2, sine pi by 2 is 1. So it's mu naught I by 4 pi R for this wire. And for this wire, it's also outward. So the magnitude, of course, will be the same. Because it's the same distance, same current, and then direction is same. So we can just add that. So B lower wire will be the same, right? Mu naught I by 4 pi R. Therefore, total magnetic field at the center is due to the semicircle plus B upper wire plus B lower wire. So that's mu naught I by 4 pi R, 4 pi R. Just mu naught I by 4 are common, right? 1 plus.
For the upper y, can you please once more say this angle thing?
Yeah, so think about this problem again. This wire goes symmetrically like this. Okay? This is a point A and this is a point B. You need to calculate the magnetic field due to this piece of wire A and B. Take this symmetric line, 90 degree. This was your S. So always remember this reference, magnetic field at this point. So with B point, we need a line, and with A point, we need a line. Then this angle is your theta 1, and this angle is your theta 2. Okay? Now look at this. This wire only has up to this point. This is missing. Right? You are here. So you are basically here, and this line is completely missing for you. Which means this theta 1 B point is here. So if you bring B point here, your theta 1 shrinks to 0. So theta 1 angle is 0. While theta 2 angle for an infinite wire will become minus pi by 2. Okay. So mu naught I by 4 pi r twice 1 over pi. So that's it, 2 by pi. So I don't expect that you really do the whole integration, but at least if you can write down up to the point where, yes, using this we can calculate, that's still good enough. Okay? So at this point, center, above, what do we have to do? First of all, you need the formula for vector field. So this is easy for, remember, for scalar potential. What was it? 1 over, for just a single charge. For a just single charge, electric scalar potential, what was it? Just Coulomb's law, just this R square becomes R, because electric field, and this has a relation of what? Okay, so this, when charge density will become just rho deta. Charge density times volume, right? If you turn it into a few like charges, charge density, not a single charge, then rho deta integration is your total charge. So this, and this is very similar. All you have to do is 1 over epsilon naught of electricity goes to mu naught above for magnetics. So 1 over epsilon naught hoye jabo mu naught by 4 pi. Etu just oporot jabo goi mu naught hoye jabo. Everything else is same. Current density, charge density will become just, you know, charge density will become current density. And nothing else. So if you remember this is easy to remember because of course you remember Coulomb's law, right? So electric field due to a point charge, how much is it? 1 over 4 pi epsilon naught Q over R square. This you remember from, I don't know, school, right? And therefore, you need to take what? This should be one derivative of R. So 1 over r square, where does it come from? 1 by r or derivative lole 1 over r square pound, right? So basically, yet ebar derivative kori to paisu. Then derivative no korle 1 over r thakibo lagibo. And 1 over r or derivative korle minus 1 over r square ahe. And there is another minus, so it will be plus. So your phi will be 1 over 4 pi epsilon naught vacuum, let's say, q over r just. So this is, I mean, this also you remember. Amar asile to potential energy asil, potential asil electric or. So it's actually remembering this is better. Then you can just take a derivative with respect to r and you get the Coulomb's law. So remember this very well. Now what? For if someone asks like, what will be the formula if there is not a single charge but a lot of charges? Just add them, right? Q1 is at R1, Q2 is at R2. Then what you do is Q1 by R1 plus Q2 by R2 plus blah, 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 right? Just that. So sum just becomes integration. If it is not a point charge just like this, at lump, then this just will become dq by r. And dq is a piece of charge. So if there is a density of charge, then density times volume is the, what is it? Number of charges in a volume is density, right? Number of charge divided by, the charge divided by volume. So if you multiply the by volume, you get charge. So dq is density times volume. Okay, you can write dv if you want, if that helps. Yeah. If that helps. I don't use because v again people use for potential and then it's confusing. Okay, but rho dv is density in case of charge. It is charge. This is charge in case of mass density. This is mass. Okay, you remember the center of mass formula, right? So anyway, so this is your potential for electric. If you know this for electric potential, vector potential is just replacing rho by j. And 1 over epsilon naught just becomes mu naught. That's, if you look at Biot-Savart's law, you'll see that it's mu naught by 4 pi. Why Coulomb's law, it's 1 over 4 pi naught, epsilon naught. So these two are again like, therefore, this will be your vector potential formula. Tower? Oh, yeah, what tower? Oh, yes, Pariba. Notation up to you. It is comfortable to use for us. Common stuff, okay. Use V. No problem. Just then, never use V for potential again. Okay. Use phi for potential then. But if you use phi for potential, then never use phi for angle. So be careful, don't repeat your notations. And if you can choose any strange notation as you wish, even Homiya letters. But just remember to define that in the beginning. Okay. Let's say co is our charge. You can do that. No problem, But just define that in the beginning. That co is the charge. Co is something else. That's fine. Just you have to define though. Otherwise,
it's you will be like you in our physics econ.
Okay. What is J here? Current density. Volume density no nai amar, right? It basically at a straight wire. So we can go to another trick. So rho dV is just total charge. J dV is total current, right? Total current. So if it is volume current, then If it is a line current, what current is line current? Just I dl. You can easily check dimensionally. So J is, remember, volume current density. These definitions must be clear in your head. So what was volume current density? If we take an area like this, how much current is passing through this? So is like current unit area. So divided by length square. And then here we have dV, volume, so length Q. So this thing has unit of what? Current times length. Right? So here it's current times length. What will happen if it's a surface charge?
IDS.
There is no I then, there is K.
Oh.
So then surface charge hole, okay. K hole K log ki thakibo lagibo. So we need in the end ideal, I into length. So K is defined as current passing through some line element. So that will be surface, right? So basically current divided by length. Right? But we want IL in the end. So K logot L square multiply korile, then we'll get IL. And L square is what? An area. So basically it will become KdA. This is simpler, just ideal. So you need to replace this JdV by just ideal. And then do the integration for dl, which is going to be complicated. It's not a circle. It's not a circle, there is no nice symmetry. Yeah, you have to at least say a few things. Okay, we can say something about this actually. First of all, final total magnetic field or direction kon pine hobo. Please tell me that. Just upward. Give me the argument why. Because then you have to explain the paper. Only then I will give you marks. Okay, simple thing hol. Eta wire karone jodi upper hoy, it's not going to be lower for the other. Why? Current is flowing in one direction, right? So moi mane iyat thagile, then it gives me upper, and then if I go to the other side, and it should not give me lower. Imagine it like a physical box, right? A line. So it doesn't matter that whether I stand here or here. It doesn't suddenly, so here it was giving me an upward, and I just changed my viewpoint and it should give me downward. That's not possible, right? Because if they are independent wires, then maybe, because maybe the current is flowing in another direction. But it's just one current that is flowing. So if I stand here, I see current going in this direction. If I stand here, I see current still flowing in this direction. So all of them should give me symmetrically, okay, right? So I mean this wire, so now is upward, it's upward. Because if you, it's upward somewhere. But not entirely upward. Because it's not, because you are at a distance from the line. The wire, if the wire was here and if you were standing here, then yes, it will give you this way. But then you go a bit this way, then circular, it will be circular, right? Direction. So, how will it be? If you draw a circle around it, maybe this way. And then for the other one, again exactly in the opposite way. Okay? So imagine like you don't have to do mathematics. Imagine like you are exactly at the center and this is one of such side. Okay? And you're going to calculate it at this point. So current is going this way here. So okay, like this. So circular, and at this point, it will be something like this. Okay? It will be like this, it will not be like this or this. Can you prove why? Perfectly like this? Because, of course, I mean, if I stand here, and if I calculate the magnetic field here, then I expect slightly asymmetric, because the bigger piece of the wire is in that way. So that will contribute more, and therefore, it will be slightly this or that. We don't know which way. But if we're perfectly at the middle, then this piece and this piece must be treated impartially, right? It cannot be bad. So therefore, we cannot be tilted like this or this. It can be this way or that way, but it should be symmetric about this. Same for the other wire. It will be this way. So that means these two, magnetic field at the center, will be, it's not coming in the video. So whoever missed the class, missed it. You can explain it to them. So for this piece of wire is going to be something like inward like this. For this piece, it will be like this. So they will be like this. So if you take this component, they will cancel each other. Only the upper components will remain. So only this. Twice, whatever the angle is easy to calculate. This height, and you know this length, then this angle is easy to calculate. So only upper. Same logic will apply for these two sides. Therefore, you will have only really 4 vectors, only the upper components added. So 4 times just because of one wire. And actually, if you are clever, then you can go backward and not calculate the vector field at all. You can just apply Biot-Savas law for a piece of wire, right? You know the angle. Calculate the B instead. Calculate the B, whatever it is, it's going to be easy. You know the angle, and you know the distance. Forget about the angle and all these things. Find out the magnetic field due to one piece, like you did for any other wire. You know, you just need this angle and theta 1 and theta 2. This time, let's say if this is the wire, then draw a line from this point. Okay, and this is your one edge, this is your other edge. So this is going to be theta 1, and this is going to be theta 2. Okay, you know this length and you know this length. You can find out what is the hypotenuse, right? So this length, and if you do, you might be able to calculate this angle, theta 1 and theta 2. Anyway, they will be same, I mean, theta 1 will be equal to theta 2, right? Just some theta and minus theta. So for this piece, you calculate magnetic field. Now just take this component, because the other one, this flatter. So it will be like this, right? Just take this one, whatever this angle, phi, this is easy to find. Just what will it be? This by this. Cos theta will be this divided by this, and you need only cos theta component. So some b cos theta. And that's it. 4 times that will give you the total magnetic field. Is it clear? I mean, do it your way. Whatever way you can calculate the magnetic field for one piece of wire. This is going to be directed like this. If this is theta, all you need to calculate is just cos theta component, because this component will be cancelled by this wire here. And again, this one will be cancelled out by the other one. So you need just cos theta 1, that is always going upward. So 4 times that will give you the magnetic field. Once you know the magnetic field, the relation is B equal to del cross A. So in principle, we could calculate A from B, but that's not what people do really. We calculate A, and from that we calculate B, because it's much more complicated. But anyway, try something, show something, do something.
Alright, so let's continue.
Yeah. But this is same logic you can apply here. What we applied for Betzov's law, same logic we can apply here for vector field, and we can do the calculation. So remember how we calculated for a circle. Same logic you can apply. It's between circle and wire. Circle because the angular things, how they cancel, that logic will come from the example of circle. And wire, how we treat the wire, these angles and all this thing, will be the magnetic field calculation for a long wire. So it's slightly difficult problem. I agree. It's longer. It will take time. But you should try. Once you do, and you solve it. Yes, it's a vector. It's a vector, right? So logic that applies to magnetic field will apply to this vector field also. Right? Any vector. If I say that there are some charge sitting here, uniform, what is the electric field here? Okay? If the problem was like some charge density sitting here, linear charges, nothing is moving, just steady charges. Calculate the electric field here. The calculation is absolutely the same. Because it is vector. So for any vector, this cancellation logic will apply. So if you calculate it for one wire, eta wire or karne hole, just upper component to low, it will be 4 times that. Okay. Next. Consider radius r, some current flowing upward, density given by J equal to what? I naught and minus
R divided
R nahi R square. R ase? Okay. R divided by tau. That's it. Tau. R divided by what? Oh, R. No, Z to tomar direction just. It is follow the Z. I not constant. Yeah, what do we have to calculate?
the total current flowing in the Z direction at any point in the wire. Calculate the current.
In the way. Okay, any point. Any point. So what is the total current? First of all, once again, definition of J is current passing through a perpendicular area. What is your area? This is your area, right? So what is the current that is totally passing through this? This is just an integral of, so I equal to total J dot dA, the flux of the current perpendicularly crossing. That's why dot. So this is definition of current actually. J is defined as di by dA perpendicular, or di equal to J dA perpendicular. So J dA perpendicular is nothing but J dot dA. When you take a dot product, you get only the perpendicular component. Remember? So this is your current. This formula you must remember. This is easy if you know the definition of J, then this is easy. So you need to calculate the total current. So we need to have a area element, right, to calculate total area. And in symmetrical situation, the most intuitive area element is just a small annular disc like this. That we can increase its radius and it will become the full area at some point. So take it at some small r distance and the thickness of this is dr. Then, so our j is what? I naught r a to the power r by r. And what is its direction? This is its direction. dA direction, obviously upward. So we can write, so dA vector is dA magnitude by into g gap. Okay, dA, what is the area of this thin element?
Twice I add into x.
Yes, dr. So length times the thickness. So I naught is a constant, comes out, r it is a minus r by r. C dot product way 1 হয়ে যাব dA whole 2 pi r dr, right? So 2 pi I naught is just r square e to the minus r by r dr, and integration is from 0 radius to the full radius. So 0 to r. This becomes 2 pi I naught 0 to r squared to the minus r by r dr. So if you do this integration, then it's done. There is a trick, easy trick to do such integration. So you can do this integration, right? A to the minus some ax, let's say dx. Right? This integration you can do. It's just exponential. It will become 1 over minus a, and then e to the minus ax from whatever limit a to b. So this is what? 1 over minus a, and then e to the minus ax, a to b, right? That's the answer. If you know this integration, then this is easy. There is a technique in physics. We can do this easily. Mathematicians will not like it. But this is valid for if a is positive. The trick that I'm telling you now. Okay. So try to remember. So the trick. Okay. Let's say our I naught, standard one, is just this. Okay. Then our actual integration is, here we have an x, let's say x e to the minus ax first, dx. This we have to calculate. We don't need by parts and all this thing. There is an easier way. How can you, let's say you have this. How can you get an x here from this? Down here. Multiply korile x kene. X te multiply koribo noaru. But we can multiply by some constant, not by x. What happens if you take a derivative with respect to a? dda. Then what will happen? So del a basically. What if I do this and at a minus here? So this derivative, of course, is a partial derivative. It will treat x as a constant, but it will act on a. This is a partial derivative. So it will just see a and it will treat x as a constant. So what will happen basically is a minus x will come down. If you do this, what will happen? A minus x will come down and e to the minus ax will remain dx, right? And then minus minus plus, and you have your actual integration. This one, sorry. Yeah, this basically is equal to this. Is it clear? X is basically this. Now, if there was x square, I could do twice this. Right? And then minus 1 square here. Just to be sure, because 3 times x cube, then I have to do cube. And then another minus will come. Okay? So this is so now look at this integration. Same, right? So let's just, therefore, let me tell you something. This we can take outside, because this x on A and not on x. So now what happens, let's do it for only one x, okay? So now we can take del del A outside, and this has become del del A, and this integration will remain. Right? And you said you can do this. This is just integration of an exponential. What is the answer of this integration? So del del A minus 1 over A, and then e to the power minus ax, some whatever, can't use A really, I shouldn't have used A. I don't know. x1 to x2 is better. So sum x1 to x2, x1 to x2. So the point is, you just do this integration. You have some result, and then take the derivative with respect to A, and that will be your answer for this integration. X times. Okay, this integration. So this we so just focus on this. We cannot. Let's say this is difficult. This is difficult, right? We can't do this. It's one time you do it, and later on, by applying it multiple times in kinetic theory, in quantum mechanics, you will encounter this thing again and again and again so many times that you will understand the importance of this thing. Because then what we'll do? There will be integrations like this, standard. You will remember the answer to the standard integral, just a few, 1 or 2. And then you can just realize the power of this thing. This can be x to the power n actually, and you can still do this. All you have to do is take a derivative n times, and then always have to do just one integral. And this integral, you just remember the answer. And when you put the answer, you just take the n time derivatives, that will be your, I mean, you are saying this is difficult. But what about this integration? Is it easier for you? It's not easier, right? So this trick will make it easier. You don't have to remember, otherwise you will be remembering like, okay, x e to the minus x or result e2, x square or e2, x cube or e2, x square 4 or e2, then it's much more difficult. So this is a... Okay. So here, in our problem, we have just square. So just square. Just square. And then the same integration. Do this integration, and in the end, put a equal to 1 over r. Right? Your a here is 1 over r. Then you have the answer. And what are the limits here? 0 to r. 0 to r. Right now, minus plus. এই ইন্টিগ্ৰেশ্যন বিলাক বহুত প্ৰেক্টিছ কৰিব লাগিব তোমালোকৰ because really physics is just a lot of mathematics, integration and this thing. This should become fun for you, like fun. Solving a problem should become a fun activity. So, etu derivative role uporor part 2 minus r e to the minus ar. This is 0, a thakibo. Then next part minus e to the power minus ar minus 1 a square. And last dot, if I put a equal to 1 over r, this will become minus r 1 over r 1 over r minus e to the power minus 1 over r 1 over r square. Let me put here. Minus, what minus was it? I don't think there was a minus. Yet minus also like it. Just one moment. Yeah. So if I put yeah, and so there is an I naught. So basically, এইবিলাক practice করে করে তোমার মনত থাকিব. What are the values of the standard integration? It doesn't take much time really. 5 minutes maximum. And this A integration too. You need to remember the answer for this. Okay. Episode just derivative. Derivative lo like kiman time lagbo? 2 minutes, maybe 10 minutes. Okay. Anyway, so this is your total current. Aru ki asel nge kiba part asel nge problem to. এই প্রবলেমের পার্ট
এটা আছে পার্ট আৰু calculate the curl of the magnetic field due to this current anywhere outside the wire at a distance of d particularly away from the center of the wire.
It sounds long, but you already have answered. So, curl of magnetic field. What is curl of magnetic field? No. You not J. And J is given. So answer is given. Oh. Look. Where or current standard bilak monot thakile you will be able to do it. Ei karone moi koisu. Where to monot rakhiba formula. Circular monot rakhiba. Okay? Remember this. Theta 1, theta 2. Remember this. And
Q dot I by
so all the standard solenoid or karne circular karne egulo jodi monot thake you will be able to do it. What is the charge density in the wire at any point? What is the charge density at any point in the wire? So, think about charge density and current density ki relation ase. Ami use kori solo bag. Yes. See, already clicking. That's what practice means. So, তোমাক J দিছো. It's just a problem of calculate the divergence of this thing, right? So, তোমার এটো divergence calculate করিলে. So, only R dependence. Look, only one R, right? So, divergence formula, cylindrical divergence in cylindrical coordinate. Anyway, tomar e just e to the power minus r or derivative lagibo, nothing else. 1 over r del r of r dr. Is it? Okay. So just tomar ki lagibo 1 over r eta ase yar. Ei part to just derivative lo, right? This is just the only r dependent part. Ei will a constant hoy ai jabo. So del dot j is basically 1 over r, del r of this will be del r of r e to the power minus r by r. Right? So constant I naught sin omega t aru 1 over r eta ase. And this will be e to the power minus r by r minus 1 over r eta ahibo e to the minus r by r. So this is your r regule. This is your divergence, right? That means what? This is your minus del rho by del t from continuity equation, right? If del dot j is this, then del dot j equal to minus del rho by del t. And what you have to do is calculate rho. So just integrate this, right? But then integration is easy because none of them depend on t. So just sin omega t integration. So all this is just r dependent, I naught. Let's call all of this together some constant here and sin omega t. So minus del t of rho equal to this, right? Some constant, let's say some constant. And this constant is, let me just put it here. Constant is I naught So it is constant ase. Forget about that. Del rho del t is this. So basically del rho is del t minus integration of sin omega t. How much? Minus cos omega t. So your rho of t will be, yeah, that omega ego, of course, right? 1 over omega integration of carne sin omega t plus some other constant of integration. And that's your answer for charge density.